Example 2. Find the value of the area between y equals x squared, which is a blue parabola, and y equals square root of 15x minus 14, which is a square root function that starts at positive 14 over 15 on the x-axis. Now we've been given the intersection points. The intersection points are at x equals 1 and x equals 2. So we have those two intersection points at A and B, and what we want to find is that area in between these two curves. So this area in here is what we want to find. So to do this, we need to set up the integral, and we need to set up the integral with the right bounds. So the area that I'm looking for is equal to the area under the curve from x equals 1 to x equals 2. And when I do this, I need to do the upper bound minus the lower bound. So the upper function is the square root function. So it's going to be square root 15x minus 14. And then I'm going to subtract the lower bound, which is the x squared function. And then I'm going to multiply that by dx and sum this all up. So finding the antiderivative of this, it's 15x minus 14. The power is positive 1/2. So I'm going to increase the power by 1 to get a power 3 over 2. And I have to remember to divide by that power, 3 over 2. And I also have to remember to divide by the 15 coefficient. Okay, so I'm just going to highlight that. Divide by 15 comes from that horizontal compression of times by 15. And then minus x cubed over 3, and my bounds are going to be from 1 to 2. So simplifying this out a little bit, I'm going to end up with, 2 over 15 times 3 is 45. 15x minus 14 to the power 3 over 2 minus x cubed over 3. And my bounds are going to be from 1 to 2. So I can now plug in my bounds. So when I plug in 2, I end up with 15 times 2 is 30, minus 14 is 16. I need to do that 2 in the denominator is a square root, so I'm going to take 16 square root and then cube it. So I'm going to end up with 2 times 64 over 45 minus, I'm going to plug in the 2 into there, I'm going to get minus 8 over 3. So that is the first part, minus the lower bound. So when I plug in 1 into the lower bound, I get 15 minus 14, which is 1. 1 to any power is 1, so I end up with 2 over 45 minus 1/3. And again, make sure you use your brackets appropriately because that's really ends up being plus 1/3. So grouping some of this together, I end up with 128 over 45. Okay, and then this is minus, well, in this case, I'm going to group some things together. So I'm going to take that negative 3 over 8 and group it together with a negative 1/3. Minus negative 1/3 from that is going to give me negative 7 over 3. Okay, so I'll just show where that came from. This negative 7 over 3 is just combining those like terms, those like fractions of the same denominator. Minus 2 over 45. Okay, I'm going to end up with 126 over 45 minus 7 over 3. Okay, so get a common denominator here. 126 over 45 minus, I'm going to times it by 15, so this becomes 105, 17. 7 times 15 is 105. 3 times 15 is our 45 common denominator. And then this gives us the total area. When I do 126 minus 105, I end up with 21 over 45, which simplifies to 7 over 15 when I divide the numerator and denominator by 3. So the area in between those two curves is 7 over 15 units cubed. Okay, so it's not a very big area there. And we've solved this by subtracting the upper bound minus lower bound and then integrating it with the boundaries. Now, in the next video, I've just put in another video in case we need to solve for this algebraically. We should, to be able to find the intersection points to get our bounds of 1 and 2, we will often have to do that. So we should be able to solve these polynomial equations. This one ends up being a fourth degree polynomial, so it ends up being particularly difficult, but I've shown a solution to that in that next video.